getting like 100 on
All right,
the
thanks for hanging in there.
so we could just have it. We had 4 people, so we want to do like 2. We've got like
Not
2
too
big
much to go over today.
Right. One of the people, she does the shop. Joey, she's living here.
So reminders. So really only other assignments left for this semester. Money's Point this weekend and the next. This assignment, CPE, your last unit assignment, that's the final exam review assignment. You can take it anytime that you'd like. It'll take your highest score. There's also the midterm version, which is available for practice. Score doesn't count for anything, but you can also take it as many times as you'd like. Then Tuesday, we'll review for the exam. Wednesday, your project submissions are due by 11:59. The assignment is available, and I've also updated it so you can see the rubric used for grading. And so you'll basically post a discussion post with your digital deliverable attached, so that will allow for potentially other people from the class to view your creative project. But the only ones that are sort of obligated to view it will be the 3 assigned peer reviewers. So then, so that'll be Wednesday. Then Thursday, Friday, and Saturday, you'll have access to stage 1 of the final exam. If you would like to come into class during that Thursday period, that's fine. You can do it here, I'll be here, but it'll be available for all 3 of those days, Thursday, Friday, and Saturday. It'll be, you'll have 90 minutes to do it, exactly the same as the midterm. The peer reviews then for the final projects are due Saturday night. Each one of you will be assigned 3 reviews. So you have to basically look at 3 different discussion posts. Instructions for how to do the peer review are on Canvas. I've done peer reviews in Canvas for a bunch of other classes, but I've never done them on a discussion post. I think the process is basically the same that I'm familiar with, but it's a little more hidden because I think when you go to the discussion post to access your peer reviews, you have to like hit the 3 buttons, the sort of kabam button, I think they call it in Canvas, to get the peer review section. Otherwise, when I assign them, I think in your to-do list, it will pop up. You've had 3 reviews assigned. Then I will review the peer reviews, and if you've filled out the numeric rubric for all 3 cases and provided a couple of sentences of constructive feedback, then you'll get your full credit for the peer reviews. And then the 3 peer reviews for each project combined with my assessment of the project will end up being the grade for the project submissions. Then stage 2 of the final exam will be during finals week. Again, I'll be here during that period if you'd like to come here to do the group exam. But so this room will be open for that. But otherwise, I'll make it available at least Monday, Tuesday, and Wednesday, probably the other 2 days. Unless, as I'm doing the exam, I see some reason why that could cause a problem. But because it's auto-graded, I don't see a reason why. I don't just make it available for the whole week. I'll know for sure once I finalize the exam. So by Tuesday, when we do the exam review, I don't know why I said that's Monday. By Tuesday, when we do the exam review, then I'll have a definite answer for whether it's Monday, Tuesday, Wednesday, or just all of finals. So change that to just say that's Tuesday. Then there is this bonus activity on April 24th at 6 p.m. as a webinar. You have to register to get the Zoom link. There's a short Canvas assignment that asks a couple of questions about that. But if you do that, you'll get 5 points out of your reading exercise column. Otherwise, course evaluations are due by Thursday at 11:59 p.m. during the last week of class. That's next week. There are dates and links on Canvas for all of these assignments. And oh yeah, and then like I said, the only other muddiest point, I do have a final muddiest point, which is the Saturday after the last week classes, between that and finals week, for which you can reflect on sort of the whole course, sort of the muddiest point, the clearest point, and so on. And then that will be the sort of the last thing you're responsible for other than the exam. So any questions about the timeline moving forward? Okay, so hopefully pretty clear. If you have any, we'll be meeting with somebody for office hours on Monday just to go over some last minute project stuff. If you would like any feedback on your project before you turn it in, let me know. I'm happy to take a look at what you've got, or any ideas or anything you need stumbling blocks you're running into. Just feel free to reach out. Happy to make an appointment, or if you want to send someone over email, that's totally fine. Otherwise, if you feel pretty confident about it, then that's great too. I wanted to, before we kind of close out with this resilience chapter, which hopefully felt like a little bit of review and maybe some perspectives, I do want to just make sure we get to scale-free networks, which is something that, and then try to connect this networking stuff to the resilience stuff. So something that from last time is we're just finishing up talking about small world networks. So can somebody remind us what a small world network is, roughly speaking? Anybody remember the rough definition of a small world network? Even a sort of Kevin Bacon inspired definition. Yeah.
Well, the small world in that example, the small world is kind of like the movie celebrity realm.
Mm-hmm.
And it suggested that if you don't have some sort of movie in common with Kevin Bacon, then you're not necessarily, you haven't like gained a sense of validity in that
Sure.
realm. So basically it shows that there's a lot of interconnectedness and lots of, I forget the word that we use, but like lots of modularity kind of.
Okay, yeah, so in that Kevin Bacon example, I think the idea was that like if you're not separated from Kevin Bacon by less than say 6 links, you're probably not a legitimate person participating in the movie actors network. I think that's sort of the idea there. Like I probably am very far from Kevin Bacon because that's just not my industry. But if I was in that industry, then the idea is that everybody in that industry is probably within 6 degrees of Kevin Bacon. So the small world networks have the sort of small world property, which sort of roughly speaking, or I'll use the same definition that I used last time, is that that we have relatively few. So it's for the size of the network, we have sort of relatively few long-range connections but a small average path length. And this is relative, when I say relatively few, that's relative to the size of the network. And so you have a very large network, but so, say in other words, we have a large network with few shortcuts through the network, and yet a small average path length. And you can think of this like, if we think about air routes, this is sort of an example of that, is that if I want to get from one place to another, there may not be a nonstop flight. But even if I'm in a location that doesn't have a nonstop flight to really anywhere, I probably don't have to take more than 2, maybe 3 hops. And that's because of what's special about the airline network that pretty much facilitates this thing that we never have to take. If we need to get from some very small town with only a tiny regional airport in sort of rural California to some very small town in upstate New York, we probably don't need to take more than 4 planes to get there, and probably less than that. So what innovation or what sort of property of the airline network allows that to happen? Hubs, that's what I'm looking for, right. So, so air routes would say hubs make this happen. And so that is what we mean by there's these sort of shortcuts, is that I may not have a direct way to get from one place directly to another, but I have a shortcut that gets me to a place that has a shortcut that gets me to any other place. And there doesn't have to be that many hubs, but as long as those hubs are highly connected, then those shortcuts exist. So there's relatively few long distance links relative to the size of the network, but those long distance links create these shortcuts, these fast paths through there. Southwest Airlines actually experiments once, when there's a bunch of empty space on consumer air that they fill up with cargo. You never know exactly how much free space you're going to get. So there's a bunch of cargo that's just waiting there, and you see how much space is left over, and then you load it on the planes. And so just in time, you have to decide, should I put this piece of cargo on this commercial consumer airline that happens to have the space for it? And for a long time, what people did is they'd say, well, I need to get this from Phoenix to New York. So I'm only going to put it on air that's going to go from Phoenix to New York. And so I wait for space to be available on something moving in the right direction. What Southwest found out, they actually used a simulation model to do this. So they tried a bunch of different ways. You could randomly put, you could just put it on any plane. You could put it on planes that, whose flight indices start with a particular number. You come up with a bunch of different policies for where to put cargo on planes. And when Southwest did that in simulation, they found that they could minimize the time it took for an item to get from source to destination if they used a simple rule. If there's a plane heading to that destination, put it on that plane if there's space available. But if not, put it on any plane. Doesn't matter, just whatever plane's available, get it in the air. And the reason that worked is because of this sort of small world property. Because if you don't have a direct path from your source to the destination, if you just get it on a plane, that most of the planes that aren't going the direction you want will be going to a hub. And so then that cargo will land at a hub, and at a hub, there's almost definitely going to be a plane going to where you want it to go. So rather than having it hold for some rare event in some small town where you're trying to get it out of, get it onto a plane where it can go to a hub, even if the hub's in the wrong direction, because that hub is going to be much more productive for it sitting there. And so that idea of just getting it in the air works because of these sorts of properties. So, so that's sort of an interesting property there, this small world property. Is that, and I think the example that Melanie Mitchell gave was, you could imagine, a bunch of people in a very simple network that's based on space. And so you can imagine that these are all people that live near each other. And so this person lives near this person, lives near this person, and so on and so forth. And so if this person needs to get a letter to this person, they can pass it to their neighbors, and eventually it gets all the way around. But what Duncan Watts and Steve Strogatz figured out is that, well, if you randomly replace a couple or a few, so let's say 5% of links with random links, I'll say random links, that's fine. Then you get a network that looks very similar. Maybe I'll just, I'll draw the whole thing again. And so maybe it looks like mostly the same, but maybe the link that used to be here, you get rid of, and you randomly create a connection that goes to some other random node, like this one over here. And so now you've got this, you've killed this link and you've introduced this link. And if you do that to just a few links in the network, turns out not, 5% is enough, then you'll go from having a very large average path length. So this is a large average path length. to a small average path length. And that's because of these long distance connections, shortcuts. And so this is one potential way to create small world networks. Now, does anybody remember from the Mitchell text what they found out? Like, they did this and they said, oh, but you know what? It turns out that it doesn't look like this is what's going on in real life. How did they conclude that? Does anybody remember? There's a network property that we defined that we said you can measure this about networks. And very often you compare it to real networks. And if they don't match up, then maybe the process used to generate that isn't what's going on in real life. Do we remember? So it's the degree distribution. So it turns out that if you do this for a bunch of randomly generated networks, and you study their degree distribution, then this here, even though it creates small world networks, which seem to be what we've got in reality, it has sort of the wrong degree distribution. Can somebody remind me what a degree distribution is?
Yeah.
Well, the degree of a node is how many links are coming in and out of it. So I guess the degree distribution would be how they're distributed.
That's right. It's, how the, so exactly, you said it perfectly. The degree distribution is, the degree is how many links each node has. So all of these nodes have 2. And the degree distribution is how the links are distributed across all of the nodes. So in this case, all of the nodes have 2. In this case, most of the nodes have 2. There might be, maybe still all have 2. But so if you create random networks and then edit them in these random ways, then you don't get the degree distribution that we see in nature. And so that suggested that in nature, we do have small world networks, but they must be a special type of small world network. And that's what Watson, Strogatz, and Barabashi, and these sort of big network people started to really sort of dig into, like, what's so special about the networks we have in nature? And so those networks that we have in nature are sort of natural, and including human systems. So natural networks are scale-free networks. And this is a type of small world network. Small world network. Okay, so we have to then define, well, what does it mean to be scale-free? Well, scale-free networks, when we say they're scale-free, what do we mean by that is that there's, on a concrete sense, if we look at the degree distribution, so this is degree, and this is frequency, and I could even call this frequency in terms of percent. That might be easier for what I'm about to say here. And so if I regard, and so these distributions tend to have distributions that have a particular skew to them that look a little bit like this. And these are called power law distributions. Which just means that if I call a degree K, then the frequency for any degree is proportional to k to the minus alpha, which I can write as 1 over k to the alpha. And where you know, very often you see alpha equal to 2. So, but in general, if this dashed line that I was got here traces out 1 over k to some power. So in this case, you know, if and this is a sort of approximately equal to. So if I meant like, you know, the degree 2 might be a proportion of around 50%. Degree 4 might be a proportion of 25%, but I could, you know, it might be a higher degree than that. So degree 2 might be at 25%, 4 might be at whatever 1 over 4 squared is. So it's the idea here that the frequency is going to decline in this way here. And these power law distributions tend to create heavy or fat tails. And fat tails are what generates hubs. So I was saying the magic of the air-lag network is it's hubs. But really hubs, you don't get that for free through that small world generation process. So small world networks is just a small world property. That's an important property, but there's a general set of networks, even without hubs, that have that. What's interesting about the airline network and a bunch of networks in nature and in human systems or whatever is that they tend to have hubs. And more generally, they tend to have distributions that look like this. And so that means that we have many nodes with few links. And we have a few nodes with many links. And those are our hubs. And that there also gives us, this is another way to get small world property. And the reason we call this scale free, notice I didn't write any numbers here. Well, the reason we call it scale free is that if I zoom out, like if I think about the web, there are web pages on the web that have thousands of incoming links. There are web pages on the web that have hundreds of incoming links. There are web pages on the web that have 1 or 2 incoming links. And so when I'm deciding my bins for plotting this out, like let's say I'm in Microsoft Excel and I have every web page in the world down a column and how many incoming links down the other column. And I want to plot this histogram in Excel or Google Sheets or whatever. Well, I need to decide where I'm going to stop this. So am I going to go from 0 to 100? Am I going to go from 0 to 1,000? Am I going to go from 0 to 10,000? And the interesting thing about power laws is that regardless of what scale I look at them, they always look like this. And that's what Mitchell showed in her book too. So there is no characteristic scale. What we mean by characteristic scale is like, there are a bunch of other processes where like I have to, in order for me to see the distribution, I need to be zoomed in to like the right scale. Like, you know, so if we're thinking of a height, for example, well, we could say like the average, you know, the average male height for an orangutan might be, I don't know, about 4 feet. And then the standard deviation is, you know, says it could be maybe 4.5 feet tall and 3.5 feet tall orangutans. So I know that all the heights are from 3.5 feet to 4.5 feet tall for all the male orangutans. Well, if I was sort of zoomed out and looking at the scale from 0 to 1,000 feet, then all of the orangutans would then be in like, I wouldn't see any of the variation because they'd all be compressed together. If I was only looking at the scale from like, you know, 3 foot 11 inches to 4 foot 1 inches, then I'd see like flat. It looked like there's like the orangutans were all of the heights. So in that case, there is a scale. Like in order for me to understand the variation in orangutan height, I need to say, okay, well, we need to be looking for roughly 1 to 6 feet in order for me to sort of see what that variation is. There is no characteristic scale in power law distributions. Of course, they're finite, so that's kind of the one, like if there's only 100 nodes, then in some ways there's a scale, but if we consider subscales of the network, like if you've got millions and millions and millions of nodes, then it doesn't matter if you're looking at all, the degrees all the way up to like 500 or 5,000 or 50,000 or whatever, they will always be shaped like this. And that is a really cool property of scale-free networks. That's what makes PageRank work. So this is, this is what enables. This enables PageRank. Because it ensures that there is always degree variation in search results. And so if I search for orangutan, then I'm going to find a bunch of web pages, some that have very little in degree, some that have a huge in degree. And it's always going to be able to sort in there, but there will be very few that have large in degree and very many that have low in degree. So if I sort and just pick out these, then those are going to be more likely the more relevant pages, and they will be up at the top and then a bunch of irrelevant ones at the bottom. So this ensures that the top of your Google search is going to have only a couple of relevant items, because it just so happens that relevancy seems to be correlated with in degree on the web. And whatever sort of subset of the web you take, you're going to get a huge variation in degree, which means of your subset, some of them, very few of them will have very many incoming links, and most of them won't have very many incoming links. That allows you to sort by them. And that's what gives us scale-free networks. So scale-free networks happen to have the small world property, but they also have all these other interesting properties, like they tend to have hubs, and they tend to have this variation in degree, which potentially is useful if you're doing things like sorting things, and so on and so forth. So it's a special type of small world network, scale-free networks. They're scale-free because there's no one right way to look at them. You look at the whole network or subset it, and they look basically the same. Are there questions about that? This scale-freeness also does tend to create sort of modularity. And it's kind of like, that's the sort of self-similar property here, where if I zoom in, I get a scale-free network, which has its own kind of little hubs. And if I zoom out, I get a scale-free network with like big hubs. So it's almost like you get these like hubs interconnecting little hubs, interconnecting other littler hubs. So you get these little modules connecting bigger modules, and so on. And so that also seems to be an interesting property that emerges from this scale-free process. All right, so questions about that? Is it clear what I mean by scale-free network? Degree distribution has this power law shape. In this degree distribution, the process that I showed on the previous slide, where you just randomly reassign links, doesn't generate this. So that was another question they had to sort of answer, is how could you build a process that would generate this? We'll get to that in a second. Okay. Now, I do want to mention then that hubs generate leverage points. Hubs are basically leverage points. So that means that there's both opportunities and threats. And so, and I guess I should say we can do the whole SWOT analysis here. So I'm going to say here that the, a strength of, and this is sort of the strength of, scale-free networks. Is that they minimize the number of long distance links. And so in the brain, that might mean like minimizing energy use. Because you can build local structures, you don't have to build these long, big structures. And so you do see scale-free networks in the brain. At the same time, they minimize I'll say the communication delay. And so they sort of are a nice kind of balance between these two things. If you only cared about communication delay, you would just say every node in your network connects to every other node in your network. But each one of those links is very costly. So instead, you say, well, let's just say we'll have a bunch of local connections that eventually reach some hub, and then that hub has a remote connection. And if we only have a few of those hubs with these really long distance links, then that's going to minimize the amount of the cost of building these networks and operating these networks while still providing us low communication delay. And so that in itself is a strength. And what's nice about that is that it means that we can lose most links or nodes to failure because only the hubs are really important for global function. So that's, in terms of resilience, this is nice because you can, if you just randomly attack a particular node or just one node goes down, a random airport just happens to close down because they're got a power outage. Well, if a random airport goes down due to a power outage, most likely it's not like Chicago O'Hare. And so because of that, you can lose a random airport, and it sucks locally, but it doesn't affect the whole airline network. So that's kind of a strength. The flip side of that, though, is that that hubs introduce vulnerability. So if you knew that you wanted to take down the whole airline network, you just attack Chicago O'Hare, right? I mean, or a storm hits Chicago. Like the fact that we put a hub in Chicago seems really stupid because of the weather that goes through Chicago, right? But people don't make decisions based on, they make decisions for lots of reasons that have nothing to do with systems thinking. You can use systems thinking to talk about the politics and the economics and so on, but people don't often make these decisions about where to put hubs thinking in the long term. And so that's why hopefully, maybe in the future they will, but now we're stuck with Chicago, O'Hare and Midway and all that, causing these major issues. Yeah.
Well, were hubs intentionally placed, or did they just happen to become more populous airports?
Yeah, so that's kind of a good question, is that what causes those things to be there? What causes this enhancement? And we're going to get to the process that builds hubs in just a second. And so you're right that, there may be that a lot of people wanted to go to Chicago, and then that eventually, Chicago became popular, and once it was a little bit more popular, then it became even more popular, and there's a positive feedback cycle. So very often that's what can create hubs, but there can also be, political forces, economic forces, lobbying, and so on that chooses where to put these really important infrastructure sites. So absolutely, how do you seed hubs? That's a great question. So hubs introduce vulnerability. So this is an example of what I would call local or targeted resilience. Borrowing from terms we learned earlier. And the reason I say that is that most of the time, when there are small perturbations to the network, power outages and airlines or whatever, you don't notice it at all in the system. But if you hit the system just right, then this hub and spoke network has a massive regime shift, and the whole thing goes down. It shifts to an alternative stable state. So this, although hubs, they create they allow you to lose the random airport and not see any problem whatsoever. So in that case, they're a benefit for local resilience. They're not so great for global resilience because there are these sort of hidden things that could happen that will cause your system to sort of degrade to a point where it's not even usable. So that's why I would say this is not an example of a good general resilience. Another network structure might have more general resilience because it might be that if you hit a random airport, it might be the number of airports you hit corresponds to how degraded things are. So if 10% of the airports are out, maybe 10% of the flights are canceled. If 50% of the airports are out, maybe 50% of the flights are canceled. That would be an example of global resilience because there's no massive phase transition where you go from, all flights are up and then all flights are down. This is sort of the other way where, really if you lose a couple of airports, hardly any flights are canceled. But once you lose the right airports, all flights are canceled. So that's what I would call this is very brittle. So, so that's kind of the downside of this approach is that it's a bit brittle. So that's what I'd say is sort of a threat. But the strengths of these are that if you want to improve airlines or maybe disease spread, you don't have to hit every airport. If you just make things better at the hubs, you're going to make things better probably everywhere. So if you improve conditions at the hubs, you're probably going to improve the conditions at the airport. Or likewise, when they, vaccination campaigns. It turns out that a lot of social networks also have this scale-free situation. So if you have a disease that's infectious, it spreads through the social network. Well, you could vaccinate everybody, but if you could just vaccinate the people who have the most friends, then you might actually be able to vaccinate a small fraction of the population and get all the benefits of vaccinating all of the population. And so that's why, Mitchell talked about there are some strategies in epidemiology where when someone gets sick, you vaccinate all their friends. And the idea there is that the person who got sick, you don't know where they sit in the network, but they're probably not a hub. But it's very likely they're connected to a hub. So not all of their friends are hubs, but maybe one of them is. So if you vaccinate all their friends, you're very likely to hit a hub. And if you vaccinate the hub, that might stop disease transmission from others. They're not saying that they got the disease from their hub, but they're saying that that's how you identify hubs. It's really hard to find out who the hub is out there. But if you happen to get one person who's sick and is willing to, to reach out, then if you can vaccinate their friends, then you have a likelihood of hitting the hubs. So hubs can be leverage points. So not only do they they make networks more brittle, they actually provide us opportunities because then if we treat the hubs, we treat the network with very little effort. Does that make sense? The strengths and weaknesses of scale-free networks? And fortunately or unfortunately, like I said, see scale-free networks everywhere. Power system, like I said, airlines, disease networks, social networks. So if you understand scale-free networks, then you have a good idea to sort of understand structures that just will see throughout the natural world, human and non. So that then suggests the question, then how to build scale-free networks. And to be honest, no one quite knows all the processes that go into building scale-free networks in nature, and how easy or hard it is for them to form. But we do know that there is one popular process that's been suggested. And so a popular idea, I would say a popular hypothesis, remember, hypothesis is an answer to a how question, is preferential attachment. And this is sort of a link-based rich get richer or success to the successful. So basically, we're back to our archetype where we've got two reinforcing loops that are sort of fighting each other until one grows and dominates the other. So, so let's say, just say positive feedback. And the idea here is that when a node gets added, it has a probability to link to another node or nodes based on the in degree of that node. And so rather than adding a node and then creating a random link to any other node, this process where whenever a new node is added to a network, someone joins the network, then who do they link to? Well, if they tend to link to those, if they tend to more often than not link to those who already have a lot of others or a relatively large number of others linking to them, then that is what we refer to as preferential attachment. And you can show that if you grow networks in this way, then this leads, this is a sufficient, not necessarily necessary, but sufficient condition for scale-free networks. So there are many other ways to build scale-free networks, but this is one way to build them. And we can imagine a lot of processes sort of been mentioned already, like maybe Chicago is just kind of more popular than other places. More people wanted to fly there. So that airport got a little more popular. And since it was a little more popular, then more routes started to go there. And that's how you got the birth of a hub in Chicago. And that might explain why both O'Hare and Midway are both, very popular airports. So that, it's a rich get richer sort of process. And that's one way to get scale free. Questions about that? So we know small world property, scale-free networks. We have a way to build scale-free networks. The only other sort of network-specific thing I want to mention, and just sort of a note that was happened at the end of Mitchell's chapter, is that the the one thing is like how networks collapse. And so this is this is dynamics on networks. So one sort of still open line of research that people are sort of trying to understand is what happens when node failures depend on other node failures. And so the problem of cascading failures is a major issue still. And so there's a bunch of examples of this. When we talk about like static properties of networks, who do we vaccinate? We just look at the scale-free properties, but that doesn't answer the question of what happens immediately after a hub dies. What other nodes are going to suddenly be overloaded and then likely die? So what is the sort of, how do we predict future node failures after subset
of nodes fail? And then how do we protect against this? And there's a bunch of examples of this. A little generator in Ohio happens to fail. Suddenly all the demand that generator was helping to provide gets pushed off to other generators just naturally in how the AC network is wired up. Suddenly those generators have much more demand, and then they start failing. As they start failing, it creates a cascade, and suddenly the whole East Coast is, a blackout where a large portion of them might be, out of power for several days. Those sort of things have happened. Texas is an interesting example because they have disconnected themselves from the North American grid. And so they're sort of an experiment in that, as the demand in Texas becomes larger and larger, then they're having a hard time keeping up with it. But we know that the spread has to stop at their borders because they can't, in that case, they might actually not fail as much if they were connected to the rest of the North American grid, because they could then bring power in. Or if things go really wrong in Texas, you cascade and take out all of the North American grid. So understanding that, would it be better or worse to connect Texas to the North American grid? That's a really hard problem to solve. And so this is sort of just kind of an important problem in network science. All right, any questions about the general idea of cascading? I'm not giving you any principles or all that. I mean, again, it's just a hard problem. We don't have quite as enough theoretical background. Even this was Melanie Mitchell wrote her book in 2009. Still, we have basic ideas, but nothing that we can really stand on, like we can stand on hubs and things like that, and those properties of scale for networks. So, but I just want to introduce the issue there that regardless of how much we know about scale-free networks, we still have a lot to learn about cascading networks. Okay. All right, so I wanted to connect this back to resilience. That's the reason why I do read this last chapter. So there's not a whole lot I have to say about this last chapter. I thought the 9 attributes of resilient systems were good. I think they're largely a review of things that we've seen in kind of the advanced resilience unit where we talked about panarchy and so on. And so just center my thoughts here. I did, one way that I wanted to bridge these 2 units is I did put a couple of optional papers online, one that was just published, I think, last week, that was an example of showing how we can use networks to generate metrics of social structures and then study how those metrics change over different gradients. And so there's this nice, so this paper, you can find it on Canvas. So this is the Montano, yeah. So this is the, and again, not asking you to actually read this paper, I'm going to give you a quick summary, but I happened to see this paper pop up in my feed, and I just thought it was a really nice example that if I could bridge these 2 things. So the idea here is that they were studying, well, so I guess the deeper idea is that there's an older paper by Burtness, and this is also on Canvas, Burtness and Callaway, 94, and they kind of established this thing called well, you can summarize it calling this sort of stress gradient hypothesis. And the idea was that they were interested in sort of sessile communities. And so there were like animals that stay in one place or plants. So if we just focus on plants for simplicity, then the idea here was that if you have, you can have an index here of, well, I'm going to call it facilitation or macrobiosis, which basically facilitation is an association between two species that doesn't hurt either species and might benefit at least one of them. So, so it might be a symbiosis, or it might just be sort of mutualism. It might, only be beneficial for one of them, but it's sort of an assortment of different species together. And so now normally if two species would share a niche, they would outcompete each other. And so you wouldn't get this facilitation. You wouldn't find two plants that share the same niche being in the same place together. The more efficient of the two plants would dominate. But it turns out that there are certain conditions where this does happen. And so in the desert, we see it a lot. So if we have increasing physical stress, so this is increasing physical stress, you see more of this. So like in the desert, you have nurse plants. Does anybody know what a nurse plant is in the desert if you're walking around? Yeah.
Those groups of cacti that sort of protect the young saplings.
That's right, absolutely. So it's idea of these plants that shade saplings. So those saplings are going to end up growing up in the same area and actually competing for the same resources as those nurse plants. So you might expect them to sort of outcompete each other, but the sun is so hot that all of the costs of competition are dwarfed by the benefits that they get from the shade of the nurse plants. So, you'd imagine that you're going to get some increase in facilitation as physical stress gets large. But in the case of plants, as physical stress goes the other way, you get increased consumer pressure. In other words, as it gets cooler and cooler out, the other animals out there start eating more of the plants. And so as you start eating more of the plants, then if you're a palatable plant, you kind of don't want to be out in the middle of nowhere. In fact, you kind of like to be embedded in a bunch of plants that aren't very palatable, because then maybe you won't get eaten as much because the animals won't want to eat the plant that tastes bad or that have toxins and things. So the idea was that you then get an increased facilitation here. So on a physical stress gradient, you should get sort of a hot spot, I guess. You should get competitive exclusion when there's low stress. But then you should get facilitation when there's high stress. And this has been tested in, again, plants and sessile communities and things like that. What this new paper wanted to do is say, well, does this maybe work for animals that have to move around as well? So let's test this hypothesis using a different model. And that model is going to be mixed species bird flocks. So you can go into forests and you look up and you can see a flock of birds. And a lot of times the birds will be all one species, but very often you'll see multiple species in those flocks. And so they went up and down the Andes mountain range, and they looked at lowland forest, and they also looked up in the montane regions, and they just looked at what birds were there. And they created these species social networks. And those basically would connect one species to another with links, which were actually what we refer to as weighted links. And so we have a link is weighted with the probability that two species are found together in a flock. And so if this is a thick line, then it's got high probability. If it's a thin line, then it's got low probability. And so if you've ever witnessed two species together in a flock, they'll have a line between them. But if you witness them a lot together in a flock, it'll be a very thick line associated with a high number. If it's not very often, it'll be a thin line. And that created these networks. You can look at these networks you can look at the networks generated in different conditions. So for lowland forest, and these are viewed as low stress environments for reasons that I could talk about offline if you'd like, and then that I also talk about in the instructor's notes, or montane regions or mountain regions. And so basically this is high elevation. And these are viewed as high stress. And they look at properties like the amount of connectivity and the flip side of that, modularity. And so what they end up finding, and I'll just sort of cut to those results. If I go over, I can scroll to are results like these, where what they find is as you go up in elevation, you go up in how connected all of the individuals are to each other, all the species are to each other. Likewise, if you go up in latitude, you get that same. And then on the sort of flip side of that, showing the same pattern, as you go up in elevation, then you get less discrete modules in the networks. So basically this is saying at high elevations, they're in these large multi-species groups with lots and lots of species. At low elevations, then they're in these not so large groups where the groups sort of are one or two different species that are very similar to each other. And I wanted to just bring this up, and I'll close on this point, is that this sort of demonstrates how we've talked about there's a link between diversity and resilience. And when you're in a situation that's high stress, there's in order for these communities to stay around, they've got to be resilient communities. This resilience ends up coming from the diversity of these multi-species groups. When you're in lowland forest, where there's not a lot of stress, then competition jumps up. And when there's high competition, it kills the diversity. So we've got low diversity when there's no stress, high diversity when there is stress. And that's just because communities with low diversity were not resilient and they couldn't survive in these high stress conditions. But those low diversity communities were extremely efficient, and they're the ones that dominate in the low stress conditions. And that was a big part of this chapter, was creating resilience by enhancing diversity and creating space, even though it comes at a cost of lower efficiency. And that's all I've got for you. We'll end there. So I'll give you all attendance credit because I was so darn late. And yeah, we'll have a review on Tuesday. If you have any questions about your final projects, please feel free to send them up, and I'm happy to meet with you about those before you turn them in. If you have any questions in class, come up. Otherwise, have a good weekend.